So let's go ahead and look at these warm-up questions. Well, I should pin myself. I need to pin myself. Did I pin myself for it? There we go. I'm pinned. All right. Now we'll do that. Cool. All right. So just one more time before we kind of move on from it. The fundamental theorem of calculus part 1. If you're taking the derivative of the integral from x cubed to e to the x of some function of t, you're just going to throw the top function in there if it's a function and get sine of e to the x squared times the derivative of e to the x, which is e to the x, chain rule, minus, now we do the bottom since it's also a function of x, sine of x cubed squared times the derivative of x cubed, again because of the chain rule, which is 3x squared. We could simplify this if we really wanted to. It's not particularly necessary here, but you can write this as sine of e to the 2x times e to the x minus sine of x to the 6th times 3x squared. And that's about as simple as it gets. Questions about that? Cool. All right. This other one here says if the derivative of e to the x cubed is equal to 3x squared times e to the x cubed, what is the antiderivative of x squared times e to the x cubed? So it looks like a good guess would be e to the x cubed, except we're off by what factor? Well, these are virtually the same. I'm just missing a what? 3. So what we could do is we could say, well, the integral of x squared e to the x cubed dx is equal to 1/3 times the integral of 3 times x squared times e to the x cubed dx. Totally valid. You can multiply by 1/3 and 3, not change anything. And then this antiderivative should equal, well, the antiderivative of 3x squared e to the x cubed is exactly e to the x cubed plus c. And you don't need to, you can write the plus c in here if you really want to. And if you distribute the 1/3, 1/3 times a constant is still a constant. So we just say plus c. Cool. So we should probably go in the direction of area between curves first. So let's go that way. All right, let's try to keep things in order here. And for those of you on the Zooms, you stop me if you have questions. So let's look at the following. Let's find the area between y equal to x squared minus 2x and y equal to 3x. So when doing something like this, it's certainly not required to draw the graph of the functions, although it is also helpful. So if you can draw it, it's a good idea to do so, but it's not necessary. And we'll talk about how you can get away without doing it very easily. So let's go ahead and draw it though. So y equals 3x is a nice straight line. Draw that in red. Something like, but not exactly this. And y equals x squared minus 2x, or as I might think of it, x times x minus 2 is an upward opening parabola that has intercepts at 0 and at 2. So it's going to do something like this. We want to find this area between these graphs. So here's the idea when you're finding any area, really. You're going to take the region that you're looking at and draw a strip. And it might be a vertical strip or it might be a horizontal strip. And which kind of strip you decide to draw kind of depends on what the shape looks like. I will say a very general statement, which is that you want to try to draw a strip, if you can, whose ends are always the same function, meaning here I would prefer to draw a vertical strip because no matter how far left or right I slide this strip, the top function is always y equals 3x and the bottom function is always y equals x squared minus 2x. On the other hand, if I drew a horizontal strip instead and slid it up and down, some of the time the left-hand function would be y equals 3x, and some of the time the left-hand function would be y equals x squared minus 2x. That's less ideal. So if you have the choice, you want to draw the rectangle or strip so that the ends of it are always touching the same function, meaning the top end is always touching this, the bottom end is always touching that. The reason being, it's going to make your calculation easier. So here's our idea. We've got this vertical strip, and really what we're doing, we're just thinking about kind of Riemann sums like we did before, where to find the area, we're going to essentially be all of the areas of the rectangles added up. And here's what we're not going to do. We're not going to write this area as the limit of the sum from k equals 1 to n of f of whatever times delta x. But here's what we are going to do. We're going to say, well, the area of that strip. Well, that's a rectangle. It's a rectangle whose height is the top function minus the bottom function, which we'll fill in a second here, and whose width is a small change in x. So the way I'm going to write this is top minus bottom times a small change in x. In this particular case, the top function happens to be y equals 3x. The bottom function happens to be y equals x squared minus 2x. And the small change in x, I'm going to choose to write as dx. You can choose delta x if you prefer, same idea. But the idea is now that's the area of one strip. And I want to quote unquote add up all the strips, all the areas of the strips. I'm just going to write strips. You know what I mean. All the strips from as far left as x equals 0. That's how far left the strips can go, right? That's my leftmost point. To as far right as, oh, I probably should have found where these intersected. To find these intersection points, we're going to set the functions equal to each other. X squared minus 3x equal to, sorry, x squared minus 2x, apologies, equal to 3x. Bring everything to the left, you get x squared minus 5x equal to 0. Factor out an x. So our other point of intersection is x equals 5. We can check if we want, right? If you plug in 0, clearly they're both 0. If you plug in 5, 3 times 5 is 15. 25 minus 10 also 15. Works. So we're going to add up all the strips from 0 to 5, meaning we're going to say that the total area is, well, the way we add up all the strips in calculus is the integral from x equals 0 to x equals 5 of your top function minus your bottom function. Or I should even say this in a more expressive way, as your function with higher y values minus your function with lower y values on that interval. After the setup, the rest of the process is usually not too terrible depending on what you've got. Here we have to, over here, I should simplify my integrand. I'm going to write this as the integral from 0 to 5 of 3x minus x squared minus 2x is going to be 5x minus x squared. And then we're going to use the fundamental theorem of calculus part 2, or we're just going to do the definite integral, which is anti-differentiate. You get 5x squared over 2 minus x cubed over 3, evaluated between 0 and 5. And then you plug in, you get 5 times 5 squared over 2 minus 5 cubed over 3. And you should at least mentally think about, if I plug in 0, what do I get? And here, in this case, you do get a 0 minus 0. But I'll warn you every time, just be careful, right? You don't always get 0 when you plug in 0. Like if you have cosine or e to the x or some other function that doesn't give you 0 when you put in 0. Fun fact, you could calculate this as 125 over 2 minus 125 over 3 and get a common denominator, which is kind of a pain. Or you could do something tricky and see that, oh, look, I have 125 over 2 minus 125 over 3. Instead of trying to get a common denominator, not that it's that hard, you could factor out the 125. 125 times 1/2 minus 1/3. To me, that's easier to deal with. That's 125 times 3/6 minus 2/6, which is just 125 times 1/6. That's how I would choose to deal with that. You mean horizontally?
Horizontally, yeah. If you show the lowest point from Y,
Mm-hmm.
so which would be our vertex for that specific problem. It's still not work.
You can make it work for a parabola. What you'd have to do is you'd have to find the right half of the parabola as a function of y and the left half of the parabola as a function of y, and there's slightly different functions of y.
Sure, but don't you have to, for example, on this one, don't you have to break out the part that's below the x-axis that's separate integral?
Yep, you have to
You
do
couldn't
two.
just add, you couldn't just minus the top from the bottom and hit the y-axis here.
No, so I will point out, we definitely could do this one using horizontal strips if we wanted to. We don't really want to.
Okay.
But if you want to talk about this one later, I'm happy to talk about how you do this one. It's a little tricky for parabolas that don't have their vertex at the origin or really on the y-axis, because splitting them into a right half and a left half is kind of a pain, but it's totally doable if you choose to do it that way. Let's look at a better example though for going the other direction. Actually, let's not quite yet. Let's look at one more example like this, where I'm going to point out how we figure out what we want if we don't draw it. So let's say we wanted to find the area between, I have to make something up. Let's see here. Sure, bless you. F of x, bless you again, equal to, sure. Oh, sorry, let me think about my favorite example here. Yeah, why not? Square root of x. Yeah, sorry, sure. Okay, that's good. G of x equal to 6 minus x. And I said I was going to do a thing, but I'm probably not going to do a thing. And x equal to 0. So one of these functions is kind of on top. What I wanted to point out is that you can figure out which one's on top without actually graphing the whole thing, although I'm probably going to graph this one anyway, by first setting them equal to each other. Well, that seems like a, yeah. Sure, I'm going to graph this one because even though this one's totally fine to do, there's something else I want to point out. So let's graph it. Here's the square root of x. Looking as good as it ever does. And g of x equals 6 minus x just looks like a line going down from left to right. Something like that. With a y-intercept of 6 and an x-intercept of 6. And I always like to point out at this point, it might not be super clear which region we want. It could be this region here against the x-axis, or it could be this region here against the y-axis. But we have a third boundary. The third boundary is x equals 0, which is the y-axis. So here is our third boundary. So we really want this region here. So we need to find, or we should find, this point of intersection. And here's what I want to say about this. You totally could find it by setting the square root of x equal to 6 minus x and solving it. And you would square both sides and then do some bringing over the one side factor, cancel. You totally get two values and one of them will be right. But here's the thing. People are often going to make these easy. They're going to make the point that, like, I don't want the answer to be 3 because I don't want x to be having to find the square root of 3. So here's the thing. We want to say, well, it's probably going to be something where it's easy to take the square root of it. So I might try like x equal to 1. The square root of 1 is 1. 6 minus 1 is 5. That doesn't work. I might try the next square number, which is 4. Square root of 4 is 2. 6 minus 4 is 2. Oh, that works. That's the point where x is 4 and y is 2. So a lot of times if you see a function that's kind of something that doesn't evaluate nicely in a lot of places, it's often a good thing to just guess the nice values for that function. Yeah.
Quick question. In both this one, if you use the x-axis, or even if you put it in terms of x to solve for y, in both cases you get one extraneous answer.
Yeah, you will.
So
Because here's the thing, if you square both sides, what you're kind of doing is you're extending this part down here. And that's where your extraneous answer would be.
Okay, and we have to just check everything out.
Yeah. So the thing is, the extraneous answer is 9, because the square root of 9 is 3, and 6 minus 9 is -3. And if you square both sides, then it totally works. That's why you get an extraneous answer there, because you're squaring both sides. So what I also want to say here is that if you didn't do this work of graphing it to see which one's bigger, the way you could figure out which one's bigger is you could test a point between your endpoints. So we know we're going as far left as 0 and as far right as 4. And if I'm going to draw, again, I'm going to pick a vertical cross section here. Without graphing it, how do I know which function is bigger? Well, on the interval from x equals 0 to x equals 4, these functions never cross each other, right? They cross each other at 4 and nowhere else. Often with these kinds of examples, they also cross each other at the other endpoint, not this example. But if you know that these are your endpoints, you can test any point in between. So you could, for example, test x equal to 2. And say, okay, well, f of 2 is the square root of 2, and g of 2 is 4. And clearly, g of 2 is the bigger value, so g of x is the bigger function. And that's something that will always work, because the functions only cross each other at the ends. Then in between the ends, one of them is always bigger, and one of them is always smaller. So this is a very easy way to kind of get around the graphing aspect of it. If it's really hard to graph, or you just don't want to graph it, yeah. So here, the area of our strip, once again, is the height of the thing, which is top minus bottom, times the width of the thing, which is dx. And then to find the total area, we're going to add up all the strips. That is, we're going to integrate from x equals 0 to x equals 4 of our top function, 6 minus x, minus our bottom function, which instead of writing as square root of x, I encourage that you all to write as x to the 1/2 power. It's going to be easier to see how to anti-differentiate that. Okay, now we're going to do it. So we're going to get that this is equal to, let's see, the antiderivative of 6 is 6x. The antiderivative of minus x is minus x squared over 2. The antiderivative of minus x to the 1/2 is minus x to the 3/2. Dividing by 3/2 is the same as multiplying by the reciprocal, which is 2/3. Evaluated from 0 to 4. So then we plug in 4. We get 6 times 4 minus 4 squared over 2 minus 2/3 times 4 to the 3/2. And then we plug in 0 and we get 0 minus 0 minus 0. And then we should simplify. That's going to be 24 minus 16 over 2 is 8. And 4 to the 3/2 is 8 as well. Right, it's the square root of 4, which is 2, and then you keep it, you get 8. And 8 times 2/3 is 16/3. If you wanted a common denominator, I guess, well, in fact, no, I don't want, I want to do 24 minus 8 is 16. 16 minus 16/3. Again, I'm going to factor out a 16 and get 16 times 1 minus 1/3, which is 16 times 2/3, which is 32/3. Or you could have just said that's 48/3 minus 16/3, which is 32/3. Cool. Okay, let's do another one. But this time we're going to go, or we're going to make different choices. So let's set up, and also this is a good reminder.
Can we try it?
That's what we're about to do. So here's what I want to mention. It is likely that when you have a first exam, or maybe a second exam, you might see a question that says set up, but do not evaluate. Don't spend time finding the area there, right? Just set it up and follow the directions and don't actually evaluate it. I've seen too many students waste 5 or 10 minutes on a test finding an integral that they didn't actually have to find. So make sure you read the instructions. Something says set it up, don't do any more work than that. If something says don't simplify, don't spend any time simplifying. Just do the minimum that you're being asked to do on an exam. So let's set up an integral for the area between the following functions. Y equals x squared, y equals 1 over x, and y equals 9. And if you can, it's often a good idea to draw a picture. Yeah. So y equals, now I should point out, right, y equals 1 over x, like this. And also there's some of it over here too, fine. I don't really need all that. And then y equals, oh, I should label things, good to label things. And y equals x squared, your usual parabola. Something like this. And y equals 9 is a horizontal line. I'm going to do this sort of deal. Now I should be explicit here. If someone says find the area between so many graphs, each of those functions or graphs or whatever has to be a boundary of the region. What I mean here is that, like, if I continue this parabola to the left here, it's yeah. So this is where the person writing the problem, me, has been not explicit enough, because technically there are two valid answers here, or two valid regions. There's this region here bounded by y equals 9, y equals x squared, and y equals 1 over x. And there's also this region here bounded by y equals 9, y equals x squared, and y equals 1 over x. So often, if that's an issue, someone will also write in quadrant 1 to specify that we only want the region in quadrant 1 that's bounded by those three graphs, not any other region. But sometimes people forget about that. So just be aware. Sometimes someone might be like, well, which region? Usually it's the one that's in quadrant 1, even if they have specified. So we are looking at this region here. And I will point out that in this case, using vertical strips is not really to our advantage. I'm going to do it first just to show you, but if we use vertical strips, we're going to have to change midway through. Because for this first half of the shape, the vertical strip to the left has a top of y equals 9 and the bottom of y equals 1 over x. So it looks like our area is going to be the integral from whatever that point is to whatever that point is. I'm not going to write the limits in just yet, of our top minus our bottom. Right? Height of the rectangle, width of the rectangle. Plus, then for the second part here, we're going to use a vertical strip like this. And now our top is still 9, but our bottom function is now y equals x squared. And then define the point of intersection. I'm a big fan of guessing and checking. I think it works out pretty nicely. It also works out, I mean, so you could find where these were like 1 over x and x squared intersect, sorry, x squared and 1 over x intersect by setting them equal to each other. But I would like to imagine that most of you could probably guess what the answer to that equation is. X equals 1. Yeah, okay, right. So that's 1 comma 1. And this point here, well, if we set 1 over x equal to 9, we're going to get x equal to 1/9. So this first half of the area goes from x equals 1/9 to x equals 1. And then this other half here starts at x equals 1 and goes up to here where x squared equals 9, which gives us x equal to 3. So that's one way we could set up integrals for the area of that region. However, we could also do it more simply with just one integral if we use a horizontal cross-section instead of a vertical cross-section. So if we use horizontal cross-sections, the same idea works. The area of our horizontal strip, well, it's going to be length times width is what I'm thinking of. So, right, so length times width. The width being the height, I guess, is another way I can use it. When I'm thinking width, I'm always thinking like the base of your rectangle. And even though it's drawn kind of in weird way, I still think of the base as like this, the narrower part. So my length is going to be the difference from here to here. So if it's a vertical strip, it's always top minus bottom. It's bigger y value minus smaller y value to get something that's positive. If it's a horizontal cross section, it's right minus left. Bigger x value minus smaller x value. So for horizontal strips, we do right minus left instead of top minus bottom. And the width of our strip is a small change in y. Which tells us that instead of having functions of x like we did here with the dx, we're going to have functions of y with the dy. Your d whatever, your dy, your dx, your d other variable, if you're using other variables, is the variable we have to be using and tells us what we are anti-differentiating with respect to. Which doesn't matter so much in this class, but definitely matters in the future when you have double integrals and you have a dx and a dy. You decide which one you're doing first. Okay, so here it's going to be right function is, well, I just said they have to be functions of y. My right function was y equals x squared, but if I solve for y, if I solve for x, plus or minus the square root of y is equal to x. Ooh, plus or minus square root of y is not a function. I need to pick which half I want. So I want the plus part or the minus part. Well, if I look at the graph, it's definitely the plus part, right? It's the right-hand side where x is positive, not where x is negative. So I want the positive square root of y minus y equals 1 over x is one of those funny things where if you switch x and y, or I should say if you solve for x, you get the same sort of function back as a function of y. In other words, if I multiply both sides by x and then divide both sides by y, you get x equals 1 over y. It's kind of neat. It's its own inverse, kind of weird. So now the total area is going to be the integral from, well, now my limits of integration are not how far left and how far right we go, but how far down and how far up we go. The lowest this strip goes is down to y equals 1. And the highest the strip can slide is up to y equals 9. Both of these things in the boxes here, if we actually calculated them, would give us the same answer. Kind of cool. What's that? It's not that bad. Let's look at another one. You're welcome. Good luck on your test. Yeah, for those of you who are in Gorski's class, make sure you get to class before the test starts, which is at 2. So if you need to leave early, totally fine. Or 2:10, I guess, right? Sure. Let's move on. Well, so we're certainly going to come back to this idea a lot because we should talk about it a bit. But let's kind of talk about the other thing we want to get to, which is the substitution method, which is certainly, in my opinion, after you've maybe tried to simplify your integrand, it hasn't worked. Substitution is usually the next place I go. So first thing first, if I'm trying to anti-differentiate something, I try to simplify it so it just looks like x to a power. If I can't get that to work, then I try something else. And that's what I would say is a very general common theme about integration, is that if something isn't working, we're going to try something else. So let's look at the next one. So for this first one, I think I want to change this up slightly here. Let me grab this other example I had. Where do you go? Other examples? There, okay, there we go. Let's say I want to find the integral of 5x to the 4th times x to the 5th plus 2. Now, in this case, we can totally just simplify this, right? We could multiply it out. So if we simplify and solve, let's see what happens. Well, the integral of 5x to the 4th times x to the 5th plus 2, we can multiply through the 5x to the 4th, right? So what I should say is you can't integrate these separately, right? You can't say it's x to the 5th times x to the 6th over 6 plus 2x. But we can multiply out first So we've got 5x to the 9th plus 10x to the 4th. And then we can anti-differentiate each of those and get 5x to the 10th over 10 plus 10x to the 5th over 5 plus a constant. And if you want to simplify that, which I do, I'm going to get 1/2 x to the 10th plus 2x to the 5th plus a constant. Okay, but then there's another way to go. So the idea behind the substitution method is we're going to make a choice of setting u equal to something. Can I spell substitution? Obviously not. Okay, there's too many I's and U's and T's. All right, using substitution. So the idea here is we're going to pick or let u equal to some piece of the integral. And the hope, the ideal case is that the thing you pick for u, its derivative also is in the integral. So we're going to pick u with an eye towards the hope, prayer, whatever you want to call it, that the derivative of u is also in the integral. That is kind of my leading motivation when I'm doing u substitution. In this particular example, there's a really great choice. I'm going to pick u equal to x to the 5th plus 2. You could have just picked x to the 5th, but I might as well carry the constant along with it because adding the constant in there doesn't change the derivative at all. The derivative here is equal to 5x to the 4th, whether or not the 2 is there. Right? If the 2 wasn't there, the derivative, would still be 5x to the 4th. So now check this out. We're going to take our integral, and usually what people do is they solve for du, the differential here, and they say du is equal to 5x to the 4th times dx. You can really just think of it as multiplying both sides by dx. Technically, that's not allowed, but everyone does it. Everyone does it. You should totally do it. So if I rewrite this integral, I'm going to write it as, I'm going to change the order just to make it easier to see things. X to the 5th plus 2 times 5x to the 4th dx. And our job when we do a u substitution is to make sure we change every single instance of x to something with u in it. You always want to deal with making sure dx changes into something with du. Well, look, du is exactly equal to 5x to the 4th dx. Great. And then the x to the 5th plus 2 is equal to u. So look what we've got. We have exactly the integral of u du. There's no x's. That's good. It's like a translation problem, right? If you're translating from English to Spanish, you don't want some English words mixed in there. I mean, right, whatever. But you know what I mean? Like if you're actually translating from one language to another, you want all one language or all one language. You don't want some mixture of both languages in your answer. So we can either have all x's or all u's, but not like some of each. And now we know how to anti-differentiate u to the first. It's going to be u to the 1 plus 1 divided by 1 plus 1. Now, here's the thing we have to do at the end. Since our original antiderivative was an antiderivative of a function of x, our answer should be a function of x. So we have to now then replace u with what we said it was equal to, which is x to the 5th plus 2. And then we're squaring it and dividing by 2 plus c. Now, the question that always comes up is, are these answers the same? And the answer is no. But the answer really is yes, they're the same enough. So if you do a different method of integration, sometimes your answer will differ, but it can only ever differ by a constant. Because two antiderivatives can have a different constant added onto them because the constant doesn't matter when you differentiate. So let's check. If I multiply out x to the 5th plus 2 squared divided by 2. Oh, sorry. Yeah, thank you. Just to check. Let's see. So squaring that out, we're going to get plus c. That's going to be x to the 10th plus 4x to the 5th plus 4 divided by 2 plus c. And if I compare it to that, x to the 10th over 2 is 1/2 x to the 10th, and 4x to the 5th over 2 is 2x to the 5th, and 4 over 2 is 2. So look, it's essentially the same answer. The only difference is here my constant is like maybe c1, and here my constant is 2 plus c2. So this is my c1. As far as we care, they're the same. Differing by a constant is totally valid. Right. Right. But now here's the thing. If instead the question was, what's the integral of 5x to the 4th times x to the 5th plus 2 to the 999th power? While it's technically possible to multiply out x to the 5th plus 2 to the 999th power, it's something that a computer could do. Multiply it all out, multiply the 5x to the 4th through, you get 1,000 terms, and to differentiate each one of them, and you get an answer. That's not the way you want to do it. What we want to do here is say, oh, there's a great u-substitution. We're going to make the same choice. U is going to be x to the 5th plus 2. Our derivative, du dx, is 5x to the 4th. So that du is equal to 5x to the 4th times dx. That's great. We totally have that. Right here, there's my du. And right there, so when I rewrite this in terms of u, it's going to be equal to u to the 999th power du. Right? Everything turned into u's. And now we know how to antidifferentiate a power of a variable. We're just going to add 1 to that power and divide by the new power, which is going to end up being u to the 1,000th power divided by 1,000 plus c. Now we're not done, because we should, if we're doing an indefinite integral, aka an antiderivative, we should always start with a function of the same variable that we start, or should we end with a function of the same variable that we start with. Since we started with a function of x, our answer should be a function of x. So we need to plug back in u equal to x to the 5th plus 2.
It all depends on how we answer it.
Right, but typically, well, the thing is, some of them are technically achievable through brute force algebra. Some of them are not. We're about to see another example, but let's finish this one first. This one's going to be x to the 5th plus 2 to the 1,000th power divided by 1,000 plus c. And that's our final answer. And you can check, right? If you took the derivative of this, the derivative of, now I'm going to write it in a way that makes it a little easier. I'm going to write it as 1 over 1,000 times x to the 5th plus 2 to the 1,000th power plus c. So I don't have to really think about even considering the quotient rule, right? It's not a quotient rule problem. It's a constant times a function. When I do that, the constant hangs out, and the derivative of something to the 1,000th power is 1,000 times our stuff to the 999th power times, right, chain rule, exactly. And look, the thousands cancel. Oh, and sorry, plus 0 because the derivative is 0. And then the thousands cancel, and we're exactly left with the function we started off integrating. X to the 5th plus 2 to the 999th power times 5x to the 4th. So it's really kind of worth noting that when you're thinking about doing a u-substitution, you're really trying to undo the chain. You're looking for the inside function whose derivative is also there. So that when you find the antiderivative, you've got this inside function, and if you took the derivative of it, you would get the derivative of the inside function also being there. So that is the motivation for how we are choosing u when we do u-substitution. We would really like to pick a u whose derivative is also there. Now, the other sort of way that we decide on how to pick what u is going to be is we pick something that's stuck inside another function. So when I look at this, I see the x to the fifth plus 2 is kind of stuck inside of being raised to the 999 power. That makes it a good candidate for my u. So if you're, but basically being stuck inside like a square root, being stuck inside of a logarithm, being stuck inside of a power, being stuck inside of a sine function, cosine function, and an exponent, all those are good reasons to pick that thing for you. So here's another example. Let's say we want to find the integral of 3x squared times the square root of 9 plus x cubed. That's a very excellent choice for you. It might not be right. Sometimes someone's going to try and fool you and give you something that's not the thing. But most of the time, if you're thinking u-substitution, picking the thing that's inside of some other function like square root or sine or whatever is a good starting place. So let's see here. So then my du dx is going to be 3x squared. And then often people skip this step and jump straight to saying du is equal to that derivative times dx. They skip this step here.
Oh, yeah.
Right, because you know you take the derivative, you're going to get the derivative of that, and then you're just going to bring the dx over every time. So here we're going to get this is equal to, well, let's see. Always make sure you change your dx times whatever, equal to your du. You have to make sure that dx transforms into du before anything else. You can't have a dx here still. It's easy to forget about that. This is going to be the integral of, well, that's going to be du. And then the rest of it's going to be, oh, that's just a square root of u. Which you always want to rewrite a root as a power. That's u to the 1/2. This is the antiderivative of u to the 1/2 times du. And then that's going to be u to the 1/2 plus 1 divided by 1/2 plus 1. We should simplify this. 1/2 plus 1 is 3/2. And dividing by 3/2 is the same as multiplying by 2/3. And then finally, we plug back in what u is equal to, and we get 2/3 times 9 plus x cubed to the 3/2 power. Let's see. Not bad. Now, it's not bad, but it does get worse. Because sometimes it's not going to be quite so easy. For example, someone might give you something like the integral of, what do I got here? Sure. Do that. X to the 3rd times cosine of x to the 4th plus 2. What's a seemingly maybe good choice for you?
Okay. The choice I would make is x4 plus 2. But
Me too. No, it's actually not that tricky. It's a little tricky, but it's not very tricky. So the right choice is still picking, and almost, I don't want to say always, but often it's good to check. If you think, well, I said,
You're not sure.
right. If you're not sure, if you think you're going to try u-sub, it's good to try letting u equal the stuff inside some other function. And it's going to work out here. We just have to make a small adjustment. So if we find our du dx is 4x cubed. So du is 4x cubed times dx. And I don't quite have that. I'm missing the 4. But we can always adjust for a constant multiple. Usually what I like to do, although people do lots of different things here, I personally prefer to make the right-hand side here look like what I have. I have an x cubed times dx. In fact, I might even rewrite this integral. So the thing I want next to dx is next to, you don't have to do this at all. I just feel like it makes it easier to see. I'm totally going to do something like dividing by 4. I prefer to say multiplying by 1/4, but same idea. 1/4 times du equals 1/4 times 4, which cancels out, times x cubed times dx. And now we can totally rewrite this. This is going to be 1/4 times du. It's going to be cosine of u. So what I will tell you is when I look at this problem here, I see that the derivative of x to the fourth is also here. Yeah, I'm off by a constant, but nobody cares. Or it's not that nobody cares, but it's that we can always fix it. So if you see that your choice for u, its derivative would make you off by a constant, but you're still getting the right power, that's a good choice for you. Right? U equals x to the fourth plus 2, du is 4x cubed. Great, I can fix the 4. Having the x cubed is what's important. So then we can totally rewrite this as the antiderivative of cosine of u times 1/4 du. It's got to be du, not dx. Most people will like to bring the 1/4 out in front of the integral because you can always bring a constant multiple out in front of an integral. You get 1/4 cosine of u du, and then we can anti-differentiate. And the antiderivative of cosine is, oh, that's the derivative of cosine. The antiderivative of cosine is positive sine. Because what's the derivative of sine? Right. Derivative of sine is cosine. Antiderivative of cosine is sine. And then we plug back in our u, and we get 1/4 sine of x to the fourth plus 2. Plus c. And again, if you check this by taking the derivative, you'll use the chain rule and you'll end up multiplying back by a 4x cubed. And then the 4 will cancel and you'll end up having an x cubed times cosine of your stuff.
So to find C, you just have to meet equal to 0. Right?
No, we're not finding c at all. C is a constant. So what I think you're thinking of maybe is if you have like an initial condition. So sometimes that's more of like a differential equation kind of thing, where they say like, for example, someone could say something like, they can say something like dy dx is equal to, let's think of something that's not too terrible, James. Let's do this. Let's do x times e to the x squared. And also y of 0 is equal to 6. Find y as a function of x. So first and foremost, if I know the derivative of something is equal to something else, to find the actual function, I have to anti-differentiate. So if dy dx is equal to x e to the x squared, then y of x is equal to the antiderivative of x e to the x squared. And e to the x squared, that x squared is trapped or stuck in the exponent. That x squared is a prime choice for a u-substitution. Derivative is 2x. We bring the dx over. We get 2x dx. I don't have a 2, so I divide both sides by 2. Say 1/2 du equals x dx. I totally have an x dx. That's going to equal my 1/2 du. And then my e to the x squared, the x squared is going to be my u. Always, 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 I prefer to deal with the dx transformation of the du first. So let me rewrite this as the integral of 1/2 du, and then we have e to the u. Bring out the 1/2 if you care to. And be careful, people tend to get stuck here or forget the antiderivative of e to the u is just e to the u. So this symbol says take the antiderivative, and now we're going to do it. And the antiderivative of e to the u is e to the u. We took the antiderivative, we got the same thing back. And then we plug in our u and get 1/2 e to the x squared plus c. Now, normally, that's where we'd be done. But in this case, they gave us an initial condition, right, that y of 0 is equal to 6. So we're going to say, okay, plug in x equal to 0, y equal to 6, and we're going to get 6 equal to 1/2 e to the 0 plus c. E to the 0 is 1, so 6 minus 1/2 equals c. The c equals 12 minus 1 is 11/2. So then our actual answer would be y as a function of x is equal to 1/2 e to the x squared plus 11/2.
If they give us that initial condition, that's when
Right. That's usually not something that comes up very often in this class, but it can on occasion. All right. This is 201. I should stop talking. I will see you all on Friday.